So we want to go ahead and break this up first. So we have the limit as x approaches infinity at 5. And that's just going to, this is never going to change. It doesn't have any value here. So that's just going to go ahead and be 5. But the part that we have to look at now is what happens to the limit as x approaches infinity of the cosine of x over the square root of x. Now the important thing to look at here is the numerator. This numerator, the cosine of x, same thing is true with the sine, but the cosine of x is always bound between 1 and -1. So now using that squeeze theorem, if I divide this by the square root of x, that also stays true. Take the limit of all of those. So now I have the limit as x approaches infinity of -1 over the square root of x must be greater than or equal to the limit as x approaches infinity of the cosine of x over the square root of x, which is less than or equal to the limit as x approaches infinity of 1 over the square root of x. Now remember, the idea is we don't want to touch the inside, we want to squeeze it. So let's look at what happens on both sides. On this side, on the right hand side, as x goes to infinity, all of this becomes 0. Same thing happens over here. On this side, as x gets arbitrarily large, this also goes to 0. So that means that the inside limit must be 0. So now that just becomes, because of the squeeze theorem, I can say the limit as x approaches infinity of cosine of x, the square root of x. And I know this is true because it is bound on both sides. And yes, both sides must be equal to the same thing for us to make this assumption that this limit here does equal to 0. So it's just 5 plus 0. So the limit is just 5. Let's go ahead and do another one. And remember, the same principle holds true here. We know that the sine of x is bounded on both sides by a +1 and a -1 that's less than equal. So what you're going to do inside here is you're going to build this function. And on the inside, we are going to multiply by x to the 5th. And then when I do that, I'm left with -x to the 5th is less than or equal to the sine times x to the 5th, which is less than or equal to 1. And now the next step is I'm going to divide, and then I'm left with -x to the 5th all over 3x to the 6th plus 7x to the 4th, which is less than or equal to x to the 5th sine of x all over 3x to the 6th plus 7x to the 4th, which is less than or equal to x to the 5th over 3x to the 6th plus 7x to the 4th. Now, same technique I'm going to use that I did on these before. Each of these on this side, and again, we're going to use the squeeze theorem. I'm going to take and multiply this times 1 over x to the 6th in the numerator and the denominator. And same thing over here, 1 over x to the 6th, the numerator and the denominator. When I do that, we are left with -x to the 5th over x to the 6th. And this becomes 3x to the 6th over x to the 6th plus 7x to the 4th over x to the 6th. And all of that reduces to become -1 over x 3 plus 7 over x squared. So this approaches 0. Now remember, when there's 0 in the numerator, we do still have to check that the denominator is rational, and it is, because that's 3 plus 0, so 0 over 3 is equal to 3, which is a wonderful piece, because now I can go back up here and say that the limit of all of this as x approaches infinity of negative x to the 5th over 3x to the 6th plus 7x to the 4th. All of that is equal to 0. So by the squeeze theorem, so let me erase some of this so I can finish this limit. So what I just showed was that the limit of, as x approaches infinity, of negative x to the 5th over 3x to the 6th plus 7x to the 4th, that is equal to 0. Now, by the squeeze theorem, this on the inside will stay the same as x approaches infinity of x to the 5th times the sine of x all over 3x to the 6th plus 7x to the 4th. And that also is less than or equal to the limit on this side, and that limit on this side is also equal to 0. So this entire limit is equal to 0 by the squeeze theorem.